Hi, everybody. Welcome. This is Miss Weeson, and right now we are about halfway through page 15 in Unit 4, and you're getting ready to listen to the fourth podcast in this unit. At this point, we've been talking about the different types of reactions, and in the last podcast, we did an introduction to acid and base reactions, and there's certainly more to come on that when we get into the actual unit of acid and base chemistry in semester 2. For now, we're going to switch gears a little bit, and we're going to talk about a very common type of reaction that you need to master, and that is called a redox reaction. A redox reaction is short for oxidation reduction reaction. And our ultimate goal here, and you should add this to your notes, is that with redox reactions, we're going to do our best and follow a series of rules, many of them you already know, thankfully, on keeping track of where electrons are leaving and coming in any particular reaction. And so in any reaction where we're tracking electrons, we call this a redox reaction. And now there's some terms to know, as you can see here in your notes. And the first one seems kind of silly, but it's an acronym, you guys, and we call that oil rig. And what that stands for, oil, is oxidation means to lose electrons. And rig means reducing, or reduction means to gain electrons. So these mnemonic devices can help you remember that oxidation, when something is being oxidized, that species is losing electrons. And consequently, when a species is being reduced, it is gaining electrons. And so we oftentimes can think in our head, oil rig. Now, there are other acronyms that you could use to help you remember which is which. Another one is Leo goes Gur, and Leo meaning losing electrons if you're oxidizing, and Gur is gaining electrons for reducing. Okay, so let's define this a little bit more. And oxidation means that you're losing electrons, like I said. And when you lose an electron or electrons, your charge is going to increase. So an example that we could use here is a neutral lithium atom. You guys know that lithium is a metal. It's got one valence electron. It'll tend to lose that valence electron to become stable and happy. In other words, to gain a +1. So in this case, lithium's lost an electron and the charge increased. Or consequently, reduction means the gain of an electron. And what's going to happen, of course, with the charge is going to reduce. And you can see an example if you jump over to the nonmetal side of the table. Chlorine, for example, is going to have 7 valence electrons. It desperately wants to become stable by picking up one more, so that outer valence shell is fulfilled and has an octet. And consequently, chlorine will then take on a -1. So you're going to see a reduction of charge. In this part of chemistry, we are now going to change our vocabulary a little bit. And instead of saying a charge of an atom, we're going to call it the oxidation number of an atom. So an example in that we just did is the oxidation number of chlorine is a -1. And the oxidation number of lithium is a +1. So when we say an oxidation number or oxidation state, we're simply referring to the charge, if any, of that particular species. So again, just to recap, instead of saying the charge on a species, we're now saying the oxidation number or oxidation state of that species. Now, in any particular redox reaction, you're going to have something called the oxidizing agent and the reducing agent. And we'll get a little bit of practice with this when we see some examples coming up here in our notes. But an oxidizing agent is simply the species in the reaction that reduced, thus causing something else to become oxidized. All right. And then the reducing agent is the species in a chemical reaction that is oxidized and therefore causes something else to be reduced. We will get some practice in just a second. Now, of course, just like with everything in chemistry, I'm going to go ahead and zoom in here. This part of your notes, the bottom of page 15, are the rules for assigning oxidation states or charges, you guys. Now, great thing is that you already know most of this. the first thing that I would actually like you to do is go to the very bottom of this little rule box and highlight step 6. Now, this step 6, this step, is the ultimate goal of balancing redox reactions. So I just will go ahead and make a note of that. So let's take a look at the rules in order. Let's go ahead and start at rule number 1. So how do you know what oxidation states to give elements? Well, in the first rule, the oxidation state of an atom in an element is 0. So if the substance is written in its element form, then there is no oxidation state. It is 0. And this includes things like or even elements by themselves, like if you've just, for example, had magnesium metal, or you had hydrogen, diatomic hydrogen, or if you had sulfur even sitting by itself. So any element that is in its elemental form is going to have an oxidation state of 0. The second step, the oxidation state of a mono, meaning one, monoatomic ion, is the same as its charge. When you look at any element in the periodic table and whatever charge it forms, that's its oxidation state as well. So we could do a couple of examples really quick. Go and find sodium. Okay, what oxidation state will sodium form? Well, sodium's in group 1 and it's going to form a +1. So therefore its oxidation state is a +1. What is the oxidation state of aluminum? If you go into the row, it's going to commonly form a 3+. So when you look at, or you can even do a nonmetal too. How about the oxidation state of bromine? That's right, it's a -1. So really, when you have an individual element, just look at what column it's in, and that will typically tell you what charge it's going to form. All right, so the first two you already know pretty much. In the third step here, or the third rule rather, in a compound, fluorine is always going to be assigned with an oxidation state of -1. So if it's in a compound, so fluorine is bound to something else, it's always going to have an oxidation state of 1. Now, that might, if you look at where fluorine is at in the periodic table, fluorine is almost typically going to form a -1 anyway, right? Okay, so let's go to step 4, or rule 4 rather. Oxygen, okay, oxygen's unique here. You just need to remember that almost always, you guys know, oxygen is going to form a -2. Look at what column it's in. It's in the column where those elements are going to form a -2. So oxidation state of oxygen is almost always going to be a -2 when oxygen is in a covalent compound. Here's a couple of examples when you have oxygen in a covalent compound. You guys remember, covalent compound is also the same thing as a molecular compound. And what is that? Nonmetals bound to other nonmetals, okay? So here's examples: carbon monoxide, carbon dioxide, sulfur trioxide. You can see that the oxygen in this case is always bound to another nonmetal. And therefore, those oxygens would have an oxidation state of a -2. Now, there's going to be some exceptions to this rule, which is why we bring this up, and that's going to include a classification of compounds called peroxides. And this is basically when you have a group, an O2 group that has a -2. Now, each oxygen is going to then be assigned an oxidation state of -1 when it is, for example, written as a peroxide. So as an example, hydrogen peroxide. Okay, the fifth rule, in its covalent compound with nonmetals. Now we're going to talk about hydrogen. Hydrogen is always going to be assigned an oxidation state of +1. And again, you kind of already know that. Look where it's at in the periodic table. It's in the column that forms a +1. There is an exception, though. You have something called metal hydrides. Okay, that is a metal bound to a hydrogen. When you have that type of scenario, you can then assume that hydrogen is going to take on a charge of a -1. So here's a good example. You would have, say, something called magnesium hydride. You would have a metal bound to hydrogen. In this case, that hydrogen is going to take on a 1- oxidation state instead of the common +1 that you guys have learned about. And so that brings us to the last rule here, rule number 6. And it's not so much a rule as a general statement, and that is the sum of the oxidation states for any compound should be neutral. There is an exception, however. For example, if it's an ion, like a polyatomic ion, for example, SO4 2-, which is sulfate, then what you should notice is that after fulfilling the oxidation rules, the overall charge of this ion should be a 2-. Okay, so let's do some practice problems. We're going to do exercise 16 at the top of page 16. Let's take a look at the first one here, and it is a carbon dioxide. I'm going to go ahead and write it with a little bit more space because I want to mark on it. Now, you guys, we have to figure out the oxidation states for each of the elements in this compound. And remember, the ultimate goal is that you are going to, I'm going to scroll back up here, look at number 6. The ultimate goal is that the sum of the oxidation states must equal 0. And the reason why is that CO2, you guys, it doesn't have an ion, it's neutral. So I have to figure out the oxidation states for both carbon and oxygen. If you go back up to the rules, look at rule number 4. And in fact, rule number 4 is going to apply here for the first one. I want you to put me on pause, scroll back up, and reread number 4 right here so you can give yourself a quick review. You already know it. You already know that oxygen typically is going to form a 2-. The oxidation state of one of these oxygens is a -2. All right. Now you see that there are 2 oxygens in this formula. So you have to find the total oxidation state for 2 of them. And so you can easily just say -2 times 2 is -4. So again, this 2 came from the formula, and this -2 came from the fact that oxygen is a -2. So oxygen, the 2 of them, have a total of a -4. Now, you then now have to determine the oxidation state of carbon. Well, because this element is electrically neutral, in other words, there's no charge, and there's only 1 carbon, then we know that carbon must equal a +4. Now, what do you get? A +4 and a -4? You get a goose egg. It's 0. It's electrically neutral. So again, charges must equal 0 if of course it doesn't have an ionic charge. So in this particular case, the oxidation state for carbon is a +4, and the oxidation state for oxygen is a -2. Now, yes, there's 2 of them to get a -4, but each individual oxygen has an oxidation state of a -2. Okay, let's try B, and we're going to be looking at sulfur hexafluoride, SF6. Just pause me really quick, go back up to the rules, and tell me which rule are you possibly going to follow here. You know for sure that according to rule number 3, and when it's written as a compound, so with another element, fluorine is always going to be assigned an oxidation state of a -1. So we know that rule number 3 is going to apply here to help us figure out oxidation states for exercise 16B. So if fluorine has a -1 for each one, so -1, how many of them are in the formula? Well, there's 6, so -1 times 6 is a -6. Okay, from this now, you can determine the oxidation state of sulfur. And to balance out to 0, and since there's only 1, we know it must be a +6. And that is, therefore, let's go ahead and write the oxidation states of sulfur are a +6, and the oxidation states of fluorine are a -1. Okay? So yes, generally speaking, you want to assign the rules of oxidation states that you know for sure. Once you do that, it will then help you determine the oxidation state for elements that might not be included on the rules. Let's do C. We have an ion here, so NO3 -1. Our oxidation states in this case should sum a total of -1. Okay, where do we start? We know for sure, according to the oxidation rules, that oxygen is always going to form a -2. And because there's 3 of them, you're going to get a total oxidation state for the oxygens is a -6. Now, you guys, what must the charge of nitrogen be to remain and to maintain that -1 charge? That's right. It must be a +5. Does that make sense? And that's because +5 minus 6 equals -1. So therefore, your oxidation states for nitrogen are a +5, and for oxygen, a -2. Okay, hopefully that's pretty straightforward. You are going to get some practice with that. Again, really knowing basic charge rules will help you here. Make a note. There can be a non-integer oxidation state. For example, in iron oxide, there's going to be a -8 for the 4 oxygens, and it's going to be divided across the 3 iron ions. Okay, so let me go ahead and show you really quick. A non-integer, you guys, is not a whole number. That's what that means. And if you look at Fe, let me go ahead and write it over here to the side, you guys, where I have a little bit more space. Fe3O4. You know for certain that oxygen is going to be a -2, and there's 4 of them. So you're going to get a -8. But then you're over here and you're like, wait a minute. What must the charge of the iron be? Well, there's only 3 of them. So basically it must add up to a +8, right? Well, consequently, because it would be a non-integer number. And so you can say 8/3 would be the oxidation state for iron, and oxygen would be have a 1/2-. Okay. All right. So let's try another example here. Exercise 17. They're asking us, when powdered aluminum metal is mixed and pulverized with iodine crystals, they add a drop of water and it helps this reaction get started. The resulting reaction is going to produce a ton of energy. The mixture bursts into flames, and purple smoke in the form of I2 vapor, so iodine vapor, is produced from the excess iodine in the reaction. The equation for the reaction is follows. My reactants are solid aluminum, solid iodine. Once the reaction goes to completion, I'm going to have aluminum iodide. It's asking for this reaction to identify the atoms that are oxidized and the species that are reduced. Then it's asking us to identify the oxidizing agent and the reducing agent. So remember, you want to go ahead and slap on these acronyms or these mnemonic devices: oil rig, or Leo goes GR, and it's GR. There we go. So oxidation is to lose, reduction is to gain electrons, that is. So what we want to look at here is go back to the formula, or to the balanced equation they gave us. And one of the rules that you're going to see here, so I'm going to highlight this first substance, aluminum, solid aluminum. Wouldn't you guys agree that this is an element with no charge? It's in its elemental form. So please go back up and understand that you are applying rule number 1 here. So scroll back up. Let's read it again. The oxidation state of an atom in an element is 0, including allotropes. Well, this isn't an allotrope, but it is a pure element by itself. So it's going to be 0, you guys. Same thing with I2. And we go over here to this compound that forms from this reaction. Aluminum's a metal, iodine's a non-metal. So let's go ahead over here. I'm going to make a little bit more space for us so we can figure out the oxidation states of each one of these. Now, what is so in this particular case, I generally start with the non-metal, okay, to determine oxidation states. That's generally where you're going to want to go. If you look at the column that iodine is in, you know that the oxidation state, which is the same as its charge, is a -1. And since there are 3 of them, 1 minus 3, the oxidation state of the total amount of iodines in this compound is a -3. Well, it's hopefully helpful and confirming that then the oxidation state of aluminum, because there's only 1 of them, must be a +3. So let's answer the question. Let's figure out which one of these species is being oxidized. So which one is losing electrons? In other words, go up to the reaction, go up to the reactants, the things we're starting with. Which of those species are we removing electrons from? If you're saying aluminum, because aluminum went from the charge of 0 to a +3. It lost 3 electrons, you guys. So that one was being oxidized. So in this case, the aluminum was being oxidized. Now, you're probably going to say and guess that the other species in the reactant, the iodine here, was the one being reduced. And in fact, it was, but let's go ahead and confirm that. Iodine went from a 0 in the reactants, and then after the reaction occurred, it went to a -1. So yes, reducing is to gain electrons. So this one was reduced. Now we're then going to ask, they're then asking 2 questions, which is the oxidizing reagent and which is the reducing agent? Well, remember, an oxidizing agent is the species that is reduced, thus causing the oxidation. So what this means is iodine is the oxidizing agent. And then conversely, aluminum is the reducing agent. In other words, it is the species that is causing the reduction. Okay, you guys, exercise 18. I'm giving you an example here where you're talking about a process called metallurgy. Basically, it's the study of metals, how we can take them, use them, process them, bend them, shape them, and do things with them. It's a great field to make some money in. You can go and get a degree in it. It's actually pretty fascinating. DU has a great program for metallurgy, FYI. Anyway, you're going to go ahead and do this one on your own. We will cover it in class. Ultimately, you're going to take this reaction that's highlighted here. You're going to assign oxidation states and determine what is being oxidized and what's being reduced. And then you're going to take another reaction from the product of the reaction above. They'll do something else, and you're going to do the same thing. Determine what's being oxidized and what's being reduced. Okay, guys, that's going to end this podcast for now. In the last podcast of this unit, we're going to learn how to balance these redox reactions by using something called the half reaction method. Okay, thank you so much for tuning in.